This one is going to be presenting combining sunrise and lunar surface interferometer observations of solar radio bursts. All right, take it away, Alex.
Yeah, thanks for having me. So this is in partnership with the whole Sunrise mission, as well as some colleagues from NES, which is focused on space-based radio stuff. So I'm going to talk through an introduction of the Sunrise mission and its primary science objectives, briefly go through how it processes its data and how we can combine it with MHD simulations, and then finally talk about some scattering concerns and how those concerns may be mitigated with the use of combining measurements from lunar interferometers. So let's get started. Yeah, so SUNRISE is an acronym, like all things, it seems, standing for the Sun Radio Interferometer Space Experiment. We're a Heliophysics NASA mission opportunity, currently in Phase C, aiming for a 12-month main science mission starting in mid-2024. It's going to consist of 6 CubeSats in geograveyard orbit, each with their own low-frequency radio antenna, and key that they can see below the ionospheric cutoff. And so with this new observing capability, they hope to localize solar radio type 2 and type 3 bursts, which are associated with the generation of solar energetic particles. So here we see type 2 radio bursts associated with coronal mass ejections and type 3 radio bursts associated with individual electron packets escaping out on magnetic field lines. The main science goals of SUNRISE are to discriminate and find which acceleration model is happening for each event. There's, to name a few different models, for one being acceleration at the shock front, 2, the shock flank, 3, the current sheet behind the shock, or 4, just diffuse acceleration throughout the compressed areas. And then the other related science objective is to track type 3 bursts as they move out. Since they aren't disturbing the global magnetic field configuration as much, they travel along existing field lines, and we want to see how widely those field lines are spread out from a given source region on the solar surface. And so SUNRISE imaging type 3 burst storms coming from individual areas will help quantify this spread through the inner heliosphere. And so a lot of this is unlocked by the equivalence of the plasma frequency. We know that the emission frequency is tied to its location, where the upstream plasma frequency is determined by the density. And so as we see these bursts move outwards from the sun and into lower, less and less dense regions, we see that emitting frequency predictably drop as well with that density. And so regular SUNRISE routines, we talk to the spacecraft once a week and download the data. It goes down through DSN, and then some pre-processing happens at JPL. And then the bulk of the science processing is done at Michigan and archived at the NASA Space Physics Data Facility. We have some test pipelines utilizing CME simulations from MHD recreations of past space weather events. And we also have simulations of the orbit constellations of the 6 spacecraft, and that interplays with the responsiveness of the array. And so we can finally push that forward and find out in the bottom right panel that the output SUNRISE fits of various simulated hypothetical burst scenarios. We can tell the difference from them visually, as you can see in that 4-panel plot below that we'll get to. So going from simulations to mock data, we have to take into account the constellation's configuration, to take into account the path lengths between the various spacecraft to combine their data in a coherent manner. And then when we combine them, we do so with each unique pair of spacecraft. So you can see the 6 colored spacecraft here in the upper right panel. And then we're taking 15 dots, because you can choose 15 unique pairs from 6 spacecraft. And each of those 15 dots, of course, has the 2 colorings corresponding to which spacecraft it's combining. And with 6 spacecraft, you get 15 visibilities, or Fourier coefficients of the sky brightness pattern. And in processing, we do an inverse Fourier transform to get a dirty image of the sky. And so this is just an overview of that pipeline. Uh, the sunrise spectra actually are generated with a channel bandwidth of 6.1 kilohertz for a total of 4,096 channels between 0 and 25 megahertz, but we're only downloading 64 of them. And we have to download very specifically to avoid uh, known ground emitters that will clog up the science data. So we have to avoid these ground emissions and also select channels such that they more or less evenly sample the range of solar distances between 2 and 20 solar radii. And so after calibration, we get out these averaged spectra that show very nicely the transient radio emission, excuse that, transient radio emission above the background. And since we have 12 signal chains across our 6 spacecraft, each spacecraft has an X and a Y polarization, we'll have nice summary plots like these, where before we combine them into images. And then we go through the process of cross-correlating the data, taking in each unique pair of spacecraft data for each channel that's downlinked and creating the different visibilities that get passed on for imaging. We
2
have
minutes.
realistic Okay, yep. We have realistic responses to these visibilities, and that is reflective of the underlying spacecraft configuration. And then that gets passed along for imaging at each of the frequencies. And we undergo lots of testing to make sure it can do that for small, compact emission. And we can tie that to a MHD simulation of radio bursts to confirm that sunrise can tell the difference between these various hypotheses of particle acceleration. The one rub here is that sunrise is really good at imaging compact radiation because its spacecraft baselines are between 1 and 10 kilometers. But as this solar radio bursts go outwards, they scatter into larger structures in the sky. And you actually need shorter baselines to image them properly. We're still good because in the first few seconds of emission, there is a polarized pre-scattered signature that sunrise should be able to see. But as time goes on, that initial burst will be scattered into a larger and larger portion of the sky. And so with short baselines and interferometers on the lunar surface, we can reconstruct that spatial brightness pattern of the large scattered bursts much more readily than with sunrise alone. So on the left, we're taking a single baseline from 100 meters of 2 antenna on the lunar surface combined with sunrise observations. And then on the right is sunrise observations alone, where you see very little signal, about 1,000 times less signal with the sunrise baselines that are much longer because of their orbiting characteristics and collision concerns. And so we have sketched out plans for small and large interferometers on the lunar surface, and they would help even more in localizing and imaging these scattered bursts. Here's a design of PRIME, which is the prototype radio interferometer on the moon for exoplanets. Here's another configuration with a 200-meter tether. And here's another configuration with a more spread out 200-meter tether with a increase in the resolution of the output images. So now it has about a 10-degree resolution at 10 megahertz. And then far into the future, larger arrays like Farside would be able to reconstruct the spatial brightness patterns with even more fidelity. So as a summary, yeah, sunrise is coming soon, and we'll be able to answer basic physics questions on how coronal mass ejections energize and create solar energetic particles. We laid out the processing and how we can combine that with various types of MHD or coronagraph data. And then combining sunrise observations with lunar interferometer observations will allow us to understand these physics even more and image highly scattered bursts. So yeah, thank you for listening, and I think I can take any questions now if there's time.
Thank you very much. So when you're saying the lunar interferometers, do you mean on the lunar surface?
That's right, yeah.
Okay. All right, and I think I missed one fundamental thing. What was the factor that you were using to optimize the orbits? Was the resolution of the early detection?
Right. So we want to have good enough resolution to constrain where the radio burst is coming from to within 1/3 of this of typical CME width. And to do that, we need 10-kilometer baselines. And because of collision concerns, the spacecraft can't get closer than about a kilometer together in their planned orbital configuration. And so you can get below that sometimes with projection effects, if most of their distance is along the sun-sunrise line, but really the shorter baselines that unlock the larger spatial structures are easiest on the moon, where you can physically place them together closely.
Okay, and so would the lunar instruments be the same configuration, or would they look different than the ones in orbit? I'm
Yeah,
thinking
I
more
think they
along the
would.
lines of mass.
Yeah, they could look more like Lucy, for instance, or in the case of Farside, they actually embed the antenna within a tether that they unroll with a rover spacecraft. Um, so it and space and for Sunrise, they are just deployable stator antennas on each spacecraft. So it could look quite different. And you
Okay,
would
and could you
also
get
maybe want to, sorry.
could you get almost real-time feedback from these, or would it take a long time to process the information that you're getting?
For Sunrise, Sunrise is not real time because it is, limited scope. We get data back roughly 1 week at a time. If you were to build up an operations loop with lunar interferometers, you could get close to real-time data and possibly advance warning via the localization of radio bursts, telling you where approximately the seed location of SEP particles would be. That's
Okay,
in the
all
future,
right.
though. Yeah.
Okay, that's great. All right, well, we have definitely run out of time because I asked too many questions, but thank you very much.